Good day and welcome to the Geo-Institute 4th Annual Live Streaming Web Conference. Today's topic will be soil improvement and the program facilitator is Jose Clemente. This is an audio web conference. You will hear the presentation through your computer speakers and there will be a PowerPoint presentation that will be shown throughout the meeting. You can ask a question through the online web conference tool at any point during the session by clicking on the Ask a Question button on the left of your screen. Type in your question into the box and hit the send button to submit your question. I would like to turn the floor over to today's facilitator, Jose Clemente. Sir, the floor is yours.
Thank you. Welcome everybody to this 2019 Soil Improvement Web Conference. I want to thank everybody who signed up. I want to thank all the speakers who are going to be presenting today. And I have a special word of thanks to Keller Foundations who signed up as a gold sponsor for this web conference. And I have a few words here that I need to read about Keller. The companies of Keller in North America are uniquely positioned to handle the most complex geotechnical construction projects nationwide. Including all services in one contract, Keller reduces client risk and ensures all aspects of a project are met on time and on budget. So again, I want to say a special word of thanks to Keller for being a gold sponsor of this web conference. On the next slide, I have a summary of the 6 presentations that we're going to listen to today. And I will offer a brief introduction of each one of the speakers. And the first one is Mr. Dennis Boehm from Keller, North America, and he'll be presenting on innovating the ground improvement design will rely on the smart use of big data in the future. And just briefly here, Dennis graduated civil engineer at Texas A&M University in 1986, and since 1990 he's working for Hewlett Baker / Keller North America, and he currently serves as Senior Vice President. So I'll turn the floor over to you, Dennis.
Thanks, Jose. And thank you, everybody, for joining the conference today. Give me a second here to pull my slides up. So this is a pretty interesting topic, right? So how do we use data? I mean, we collect data from a variety of different sources all around us, right? So if we think about where data is at and where it's collected from, it's collected from the phones we use every day, the phone I'm calling in on this conference from. The internet certainly collects data every time we go to a website and these kinds of things, and then certainly social media collects data. So if we think about if we as the construction industry and a little bit deeper as we, the specialty foundation construction industry, if we collected that data and used it to our benefit, what we could do with that. So hopefully in the next 15 or so minutes that I have your time, I'm going to show you some possibilities of the way I think we could do some things to improve what we do as a construction industry. So a brief outline for my presentation today. So I'm going to talk a little bit about where is the construction industry in terms of other industries and how we collect data, how do we use it to our advantage, how do we improve what we do as a construction industry. And then once we've collected the data, how do we use the data to make visualizations to show what we're doing on our sites and improvements and these things. And so, what kind of new things are we doing with data visualization? And then And then what it all means, hopefully, at the end is, if we collect data and we use it in the right way, what does the future hold for us? Does it help with AI initiatives? Does it help with, making better innovations? Certainly we hope that it reduces the cost of what we're trying to build and do everything, which kind of leads me into the next slide. If we look at the construction industry as a whole and how we have improved over time, there's some pretty interesting data that McKinsey Global Institute has put together for us in the construction industry. So if you don't know who McKinsey is and that consulting firm, they've been in the news a little bit here lately, but it's a pretty interesting consulting firm that has to do with innovation and improving business. So what they did is, over the course of several years, since the mid-90s until recently is 2014, 2015, they looked at improvement of the construction industry versus total economies from around the world, and certainly compared that to manufacturing. And you can see from both the top graph, which represents I think something like 90% of the countries that produce the GDPs around the world. So there's a lot of countries in there, and you can see construction lags behind quite a bit from our ability to produce goods and services per hour of labor or cost of labor that we're using. So construction industry is not really considered to be all that efficient when we look at maybe manufacturing or some of these other industries. And I would challenge everybody to think of the construction site as just an open air manufacturing facility, although it rarely runs like one, right? We could probably use data and reduce it in such a way that we can improve this with time, right? So one of the main drivers behind this lack of efficiency has to do with very large projects. We're all involved in some of these mega projects, I think, as a construction industry. And these mega projects and their massive cost overruns really plays a big part of the decline of the efficiency of the construction industry. So I know we can use this data on some of these mega projects and make them better. So let's think about all the different ways we collect data on our job sites. Could be drones, right? We use drones to take pictures, perform surveys, and look at changes and elevations and things. Like I said in my intro, we all use smartphones. We could use those to our advantage. We have job site sensors all over the place, connected to our equipment and delivery things, and we all have either a smartwatch or some kind of wearable that helps us with some different telemetrics and some other things that we could collect data on job sites. Nowadays, GPS is being used more and more. And then we also, as part of our look at the performance of constructed buildings and such, we're starting to put building sensors in those structures, right, to measure the environment, to measure performance of movement and changes and all these kinds of things. So, and if we think about all those different things that collect data on our job sites, what do we really use it for currently? Well, a lot of times we use it for early warnings. We look at we have geotechnical sort of sensors that will tell us of an early warning of maybe a potential failure that's fixing to occur or whatever. So inclinometers, piezometers in the ground, and some of these things. We use it to provide up-to-date project info. We have many people on job sites that collect this data manually, produce schedules and Excel spreadsheets and these kinds of things. And we also use, data for improvement cases, so change management. Collecting the data and looking at, changes, small changes in what's happening at a site to offer up, some evidence of change management. And then sometimes we use data for post-project analytics. Okay, so just a couple different ways to use the data there. So I would argue that we should be using data for a lot more, right? So if we think about all the different ways that we really should be using data, I think we can use it certainly for, design innovation. So innovating our design. If we're constantly looking at and evaluating data in near real time, it makes the design innovation process fairly easy, and I'll show you some case histories coming up where that's made possible. We could certainly use it to improve our quality and safety on projects, and without a doubt, I think construction industry has quite a ways to go there for both of those two things, and certainly increase efficiency and do a better job of making us more aware of the risk that we are involved in. Certainly improve our project delivery times. Like I said, this McKinsey report that I showed a couple of graphs from is really around project delivery on time with some of these bigger projects. We can use it for education and training, no doubt, and then certainly the BIM process. But we really should be thinking about reducing our environmental consumption of our resources, so fuel and the things we use to build buildings from, and structures, the cement and the aggregates and the steel. Well, what's really driving some of the use of data? It could be, customers are requesting it. It's a necessity. We're trying to improve our life quality. There's many different reasons why we could be driving ourselves to use this data in a much different way. If we think about, why do we need to collect data and how do we collect it, and some of the things that we're doing currently, we use data from soil borings. That's the first thing we look at from a geotechnical perspective. Is we go out and we take a couple of borings at a site, but we're not able to take, borings at enough frequency to really, paint a complete picture of the underground risk that we're looking at. So we need to use data coupled with borings to really evaluate and help us understand the assumptions made at the design level. We can use data and collection along with some of the borings that have been taken to really assess changes in site conditions to allow us to react a little bit faster to these changes. Well, we got to make sure that specifications in our projects allow us to do that. And we'd also use data to allow us to look at performance of the design. So are the measurements that we're seeing as we're building, say, a ground improvement solution or supportive excavation, do the measurements that we're seeing collected from the systems that we have in place, do they really make sense with what our design assumptions were? And so we can couple those with observations and things and really make a complete picture of what's going on from a design perspective. Okay? So as we move forward into an understanding of data and how it's used, we can kind of put a data cycle together, right? So I call this the plan, do, check, act cycle. So at the planning stage, we're looking at an initial design. It's based off of a few borings. We could be looking at, hundreds of thousands of square feet of maybe a manufacturing facility. And there might be just a handful of borings that have been taken that really try to describe the underlying ground conditions. So we have to make assumptions about strengths and depth and some of these other things that come along with the geotechnical information that were provided at the time when the plans are put together. So that's the planning phase. And so the do phase is when we're out actually doing the work. We have to be looking at the ground reaction. We have to be looking at results of testing that's taken place as we're building out the site, performing. Could be ground improvement. Could be just drilling holes in the ground for any type of deep foundation system. So we're constantly doing. So we're building, and we have to look at that data as coming back, and we're constantly checking it as well, right? We move into this next phase, and we have to review the data. So we have to look at, the ground reaction. Are we getting feedback from the equipment we're using at the, intended depths? Are we seeing, the proper termination criteria take place? Is the ground softer than we thought it was? Is it stiffer than we thought it was? All these can really affect, sort of the change management on the site. So that takes us into the next step, which is the ACT, right? And so the ACT phase of the data cycle allows us to, after the review of the data's taken place, is to implement change moving forward. So if we think about, our construction sites in this manner, it allows us to move forward with a complete picture of data and how we manage that. So, all right, so let's kind of go through a couple of interesting cases here. But the first thing, just show you the difference between a single report, which we probably all see, and visualization of the data. So in the single report on the left side of this graph, you can see the reaction of a vibrator that's been used for vibrocompaction on a particular site, and it's not very interesting. We're looking at one point. We don't really understand where the point was taken in reference to any of the other data points on the site. But if we look at it in terms of visualization, for the final stakeholder that might be involved in the project, we can see that we're trying to improve a site that's circular in plan. Could be a tank, could be a foundation for some wind turbine, perhaps. It's just a round foundation, and we see that there's multiple points that have been used for the vibrocompaction effort under that particular structure. And if we visualize the data in such a way, we can see that depending on what the colors represent, there's hot areas and cold areas of the improvement that's been done. Well, these hot and cold areas might represent stiffer soils, could be representative of more energy applied to the ground to achieve the required specification. So you can see how interesting visualization of the data in a complete way, really paints a nice picture for the end user versus a collection of just single reports. So the single report just being a data point and the visualization being, a culmination of that data that really provides us some useful insight. So if we kind of continue down this path and look at the different ways that the visualization's been done for the stakeholders, here's a particular project. So this is a ground improvement project where a target depth was determined by the engineer involved in the project. So could have been, improve the ground until you get to a certain, cutoff criteria. Could be to see a certain torque or something in the drilling machine that's used. But if we visualize all the data collected, we could see that over the course of this project, we saw these different depth differences across the site. And so I would say that this is a verification of scope reduction, right? So I think that's one of the...
You need to start wrapping things up because we are running out of time.
Okay, all right. And so this is a scope reduction. Okay. The next way that data can be used is for verification of scope increase. So this is the positive side of what contractors are in the business for, moving ahead that way. And though I see here that closing thoughts have been pulled up on the slide. So in closing, I think reduction of damages caused by poor quality control, we can certainly use data for our evaluation there. So reliable recording of production data, automatic verification of evaluation, so we can use it for reduce effort to check site performance, so save time and money, and clearly represents visual reports. And then, the specifications need to allow us to make changes based on the data that we collect at the site. So I appreciate everybody listening in on how we can use data to improve our ground improvement designs. Thank you very much.
Thank you, Dan. Go ahead. Yeah, I think we're going to leave, maybe come back, see if we can answer some questions later, because I want to make sure that we have enough time for everybody. So I want to move to the second presenter, which is Matt Caskey, and he'll be talking to us about mitigating shallow slope stability applications using plate pile ground improvement systems. And just a brief introduction of Matt here. Matt received a B.S. in Civil Engineering from University of Missouri, Columbia, and Master of Science in Civil Engineering from University of Memphis. And he's currently the National Director of Sales for GeoPeer Foundation Company, and he leads sales, business development, and strategic initiatives for the company. Matt, you can take it from here.
All right, good afternoon, everyone. Thanks, Jose, for the nice introduction. Thanks to the Geo-Institute for allowing us to speak to you this afternoon, and thanks mostly to everyone online that's participating in the webinar here. So today we'll be talking about ways to mitigate shallow slope stability using plate pile ground improvement systems. And progress through the slides. So when you're an engineer or an asset manager, facing a slide repair, that's something that's usually an unexpected cost. Those are things that we don't plan for, we certainly don't like to mess with. And as we have choices to repair those, they depend on many things, of course, not the least of which would be how much is it going to disturb my current operations in the case of a highway embankment or something like that. What's the long-term maintenance? Am I fixing it for a short period of time? Am I trying just to restore serviceability of whatever asset the slide is impacting? Or do I want a long-term fix that I don't have to worry about? And part of that is obviously, what's the design cost? How much is that going to affect the overall budget for future assets that I might have to deal with if I am an asset manager? It's always pretty inexpensive and pretty easy to push the soil back uphill when you experience a shallow slide, and it's usually cheap to do that the first time. So we'll talk a little this afternoon about SRT systems or plate pile systems. They can provide engineers with a final or engineered solution, and the design slide shows a couple of small diagrams of how this works. We're basically dividing the failed and sliding soil mass into smaller increments and designing it so that the plate pile itself is strong enough to support the movement of that smaller increment as it tries to move downhill. And so the spacing is chosen based on a couple things. The first one is the horizontal spacing, which is a function of soil arching. Generally in fine-grained soils, that's where we see most shallow slides occurring. And the traverse spacing is usually going to be a function of the analysis. And we have some slides later on to get into a little detail about that. So in the early days of development of plate pile systems, there was much research and development that went into it. And briefly describe what we're seeing in this picture. This was a man-made slide that was constructed. It had a concrete deck about 6 feet down from what you see on the slide, and this was equipped so that it would allow water to be flooded into this transition zone to see if the plate pile system actually works. And what was discovered during these tests as this thing was flooded and some soil was excavated from the toe of this area, that we could actually visually observe, and we got some empirical evidence that soil arching is indeed a key component into plate pile design and spacing. And that's good to see that a lot of times empirical work does validate our theory. just some pictures of what plate pile looks like. These are typically regular steel, black steel, that can be easily moved with a excavator and one guy on the ground. Not too heavy, and you can see that these are S shapes generally. Galvanized steel or black steel can be used if you have a highly corrosive situation. You could oversize the steel of the plate piles. It's no problem. Usually add an 1/8 of an inch or so for corrosive steel. Normally that is basically done in accordance with FHWA requirements for steel embedded into soil. And so the piles themselves can be S-shapes or they can be angles. The industry has kind of gone more towards using an S-shape. It's easily available and it comes in standard sizes. Usually 40-foot lengths of pile can be cut easily into 5, 7, 13, or 10-foot sections. And so the S-shapes are pretty usable, and the lengths can vary depending on the design need, anywhere from as shallow as 6 feet to as deep as about 16 feet. And it's important to note here that the plates themselves are going to be about 12 inches wide, and the lengths of the plates will vary as a function of the failing mass, as the depth of that failing mass. But the welds that are used to hold them on, they're not structural, they're not needed to be structural. They're just used to keep that plate on the pile as it's being driven into the ground. General guidelines for the suitability of plate pile systems or SRT systems, anything from pretty flat to pretty steep. 1-to-1 is about as steep as most applications fall into, and really most of the applications fall within a 3-to-1 or a 1-to-1 slope. In Texas, there's many slopes that are much flatter than that are still moving quite a bit, so they could be as flat as 7-to-1 or 8-to-1. And there have been situations where some plate pile systems have been used for slopes that are steeper than the 1-to-1, and those really kind of get into more of a temporary stability application, and we won't talk much about that during this short presentation period, but that is possible. Slide depth's usually from about 10 to 15 feet. If the slide is much deeper than about 15 feet, there's usually other ways to stabilize that slope that will likely be more cost-effective and usually would need something a little more robust than a plate pile, although we've done many projects where the slide is deeper than that. You do need to be able to penetrate into an underlying stable soil, usually into something stronger, silt or clay. You can penetrate into soils with rocks if they're pretty small, normally less than about 3 inches in diameter. They can be installed into softer rock, like some claystone or weathered shale, something that can be drilled with a roller cone. If you're in a hard limestone, it's usually not applicable due to the cost of coring that rock. Fast using normal excavation equipment. That's just a normal 315 or a 312 size Caterpillar excavator, and they can be installed with either using a hydraulic hammer that's shown in this video, or it can be also installed with a vibratory hammer, similar to one that might be used to install like sheet pile. A couple different ways to deliver plate pile systems to customers, and we'll talk about 2 of them here. One of them is for pretty basic projects. They can be done directly to the contractor, and these have chart solutions that make things quick to respond to. They can be installed usually by an on-site site contractor, or perhaps DOT or a public works maintenance crew can install these. Normally this is kind of an emergency response type application where the slide has occurred as a surprise and it has some impact on some part of infrastructure. And usually you want to deal with shallower slides, about 10 feet or shallower. And then, of course, if there's a more complex slide that has a little more, maybe a steeper slope perhaps, or more critical infrastructure or property, upslope or downslope of it, a site-specific design solution can be provided. And this is usually going to be installed in a design-build manner. And so you'd want to work with a pre-approved installer, someone that's got a little experience installing plate pile systems on past projects. Talk a little bit about how the basic projects can be provided. You know, the detailed engineering analysis are clearly always preferred, but oftentimes these slides are impacting public infrastructure. It might be impacting an industrial asset like a pipeline or a transmission line, or it could be putting commercial property in some imminent danger. And so you need a quick solution that allows field crews to mobilize to the field and to begin repairs of this slide. And to accommodate this, plate pile designers can use some predetermined solutions that are based on typical inputs from basic soil mechanics information. And these will provide the designer with some predetermined spacings, and they're going to be conservative, of course, based on 4 primary inputs. And those are the slope inclination, you know, how steep or how flat is the slope, how deep is the slide, what type of soil are we installing these in? Is it soft? Is it firm? Is it hard? And what is the required factor of safety? And in this manner, normally the designer would need to have project information provided by the customer, the person that has ownership of that slide, and then the designer would then turn the solution and specifications back over to that owner to be installed by a contractor of his choosing. So for complex projects, we talked that a little more analysis is required, and I'll go over in just a few slides here just the basics of how the design analysis is undertaken. The first step is, with the knowledge of what we believe the depth of slide is, we can go into an L pile output by choosing a plate pile length. And so for this one, this particular example, we chose a 10-foot plate pile just for the purposes of looking at it, with a sliding depth of about 7.5 feet. And so you model that plate pile in just a traditional L pile analysis, and as you're applying load to it, you would want to pre-select a deflection of about 1 inch, and so you want to see how much stress that plate pile can develop at a deflection, lateral deflection of about 1 inch. And then for this example, we see that with that 7.5 foot long depth of slide and a 10-foot S-shaped pile, we developed a shear resistance of about 1.5 kips. And so we know that now for this particular application, that shearing capacity for the plate pile is about 1.5 kips. You go back into your slide analysis program and using the composite shearing that's now provided with the plate piles, and so you would combine the back calculated phi and C information from the failed condition, insert the appropriate numbers of rows to the appropriate depth in a composite manner to develop the slope stability solution with the proper factor of safety. And so the required factor of safety can change. Sometimes it's 1.5. It can be as low as 1.2 or 1.3. That dictates the number of rows and how far up and down the slope you have to go. And it's common for some of these repairs to provide owners with options of factor of safety to see which one fits their budget better. So we got, this slide shows a bunch of different examples of applications for plate pile use. And due to time restrictions today, we're going to talk about 2. We'll look specifically at embankment maintenance and pipeline slides, although any of those 5 categories would be good applications for plate pile systems. First job that we'll look at is an example in the Dallas, Texas area, and this was at President George Bush Turnpike. If many of you guys online are in the Dallas area, you're probably familiar with this. And this was a situation where the slide occurred after an extended period of dry weather, followed by heavy rains, and that's the usual bad actor for most of these shallow slide movements in Texas. And as you can see from the picture, this is a busy Dallas road with traffic all the time. And if you've driven in Dallas, you know that's not unusual either. So the traffic lane is downslope, and the on ramp to get on the overpass is upslope. The failed mass was not impacting traffic, luckily, at this time, but it was feared that further movements would cause that to be a problem. So we went through the analysis that we described a few slides ago and found that this was medium soft soil with a slide depth of about 9 feet. And as expected from the, you probably drew that conclusion from the previous pictures, there were desiccation cracks that had opened during the period of drying that allowed water to infiltrate through there, form some slip-and sides within the expansive clay, causing the downslope movement. And the solution that was developed was plate piles spaced at with a 4-foot plate and an 11-foot pile, spaced 4 foot parallel to the slope and 6 foot up and down the slope, needing about 12 rows. About 500 plate piles were installed to repair this slide. And when it was done, it looked nice and natural, as if nothing had ever happened. Those 500 plate piles took about 2 weeks to install. No disruption to the traffic. You can see from the pictures they were able to work on the slope. When they were done, the natural finish was chosen to be just some sod that was placed down and staked in place after the plate piles were installed as per plan. And because the plate piles are embedded about 12 inches below final grade, there's nothing that would impede a mower or any type of maintenance equipment from doing everything that it needed to do before the slide had occurred. Next example we'll look at would be a pipeline slide that happened in northeast Kentucky. And if you guys, anyone in that area, you know that there's a lot of pipelines in the midstream industry coming through there. Hard to see from this picture, but there was a bulging slide that was moving downhill. The pipeline operator noticed there was some strain buckling in one of the pipelines, and they came up with a temporary repair method to fix this. They had to excavate soils around the pipeline, make necessary realignment of the pipe, and then replace the backfill. But the backfill, due to the emergency response nature of the repair, they had to put that in pretty quick and didn't compact it the way they wanted to, and so they needed a final repair. And you can see from the yellow on this slide, this was all the excavated material that was replaced, and they were getting a slide that was occurring. It's shown in the green towards the top of that slope, and those blue circles show where those pipelines are running with respect to this downslope movement. So the initial repair were made, but they needed a final repair so that this wouldn't continue to happen and continue to impact these pipelines. It was determined that this slide depth repair was to be about 5.5 feet, and due to the length of this repair area downslope, they needed 19 rows. This one was a little more severe. Even though it was just a 3-to-1 slope, they still needed the plate piles to be installed on 4 to 4.5 foot centers with 10-foot piles and 4-foot long plates. And so in the upper left-hand part of the slide, you can see the output of the analysis, and in the lower right-hand corner shows how that overall design looked. And as you can see, the pipelines are shown in the solid lines that are running kind of southwest and northeast, and you have to adjust the plate piles so that they're not too close and not impacting those pipelines. Overall, there was about 1,500 plate piles required for this project, completed in about 25 days. They got a period of pretty good weather, and because it was a 3-to-1 slope, the installation equipment was able to access this work area with conventional equipment. They were using an excavator to install them. The upper right-hand picture shows the excavator using a vibratory hammer, and the equipment that's on the left-hand part of the slide shows a pre-drilling rig that was required because in this part of Kentucky, the lower...
Matt, you need to wrap it up. We are running out of time.
Yeah, so with that job went well, a little bit of pre-drilling was required. So right on time, Jose. Just finish with a few parting thoughts on plate pile systems. They're fast and economical. They can be used very quick for emergency repairs due to the simplicity of the design. Most of the pictures did show conventional excavation equipment. These are things that most public works and DOTs have easy access to. And from an engineering standpoint, they do represent a final and robust repair for recurring slides.
Thank you, Matt.
Thank you again.
Yeah, I think we're going to skip questions, at least for now, because we are very tight on time here. So the next presentation is back by Dr. Aaron Gallant on blast densification, influence of gas and stress redistribution on ground improvement verification. And just a brief introduction for Dr. Gallant here. He received a BS from Tufts University and graduate degrees from Northwestern University. He is currently an assistant professor of geotechnical engineering at the University of Maine. Dr. Gallant, the floor is yours.
Thank you, Jose. Let me pull up the presentation here. Yes. As Jose mentioned, the topic today that I'll be discussing on is blast densification, and in particular, what I want to discuss is the influence of gas and stress redistribution on verification of ground improvement, and oftentimes this can be a challenge. Before I get started here, I'd like to introduce the audience to what blast densification is. The ultimate goal is to effectively change the state of the soil, and in this particular case, we're trying to change the density, okay? And how we do this is by drilling holes, burying, and then detonating explosives at depth. And what this does is induce liquefaction. So essentially, we have an unloading of the soil by liquefying the soil, and then resedimentation of the soil into a denser state, okay? So the detonation of the explosive really releases radially propagating compressive waves, followed by a decompression wave that induces shear stresses to the soil skeleton. Millisecond delays between detonation of the explosives also introduces a cyclic loading, okay, and additionally reduces peak ground accelerations, okay. And then thirdly, there's a generation of gas when we detonate these explosives, okay, and that also contributes to the increase in pore water pressure. The simplicity of the construction, which is simply drilling and then detonating explosives, makes us an economical alternative to improve large volumes or deep deposits of granular materials, okay? So this ground improvement method is really specific to granular soils with limited fines or limited plasticity, okay? So we're generally speaking we're talking about sands. How do we verify improvement? The most common method is one to survey the area that was treated, okay? And we do this by measuring surface settlements, okay? And we note quickly here that this is not a direct measurement of densification necessarily in the target layer, but if we have surface settlement, then we know something is being densified. We could also attempt to obtain direct measurements of densification through something, say, like Sondex tubes, where we're actually measuring vertical deformations at depth. And then thirdly, the other more common approach to verify ground improvement is to measure some sort of change in penetration resistance, okay? And usually this is either with the cone penetration test or standard penetration test. And the intuition being that if we've densified the soil, we'll have an increase in penetration resistance, okay? And while this is sometimes the case, we often observe either no increase in penetration resistance and in some cases a decrease in penetration resistance. In certain cases, this is followed by an increase in penetration resistance with time, okay? And what we're trying to do is really understand or reconcile these observations. So what I'm going to do today is present some field performance data from a case history, some results from a numerical analysis that were performed to try and reconcile why we're not necessarily seeing this increase in penetration resistance immediately after the ground is densified, okay? The particular site that I'm going to discuss is the Oak Ridge landfill, and this is located outside Charleston, South Carolina in Dorchester County, for those of you that are familiar with the area. The goal here was to improve a loose layer of black sand around the perimeter of the landfill, or a landfill expansion. In particular, I'm going to be focused on the northern side of the landfill, and we're going to be focused on what's considered Zone 11 here, Zone 11 on the north side. So really, they were trying to densify loose granular sediments around the perimeter of the landfill in an attempt to increase the liquefaction resistance, okay, in this particular case. Before I continue, I also want to give you an idea of the subsurface conditions, which really consisted of quaternary deposits, medium dense to dense, overlying, again, this loose deposit of black sand that you see there at elevations from approximately 23.5 to 19.5 meters, as shown by the cone penetration results on the left side of this figure. Okay, underneath that was a really dense, heavily overconsolidated marl that helped confine the layer. There was also a thin layer known as the Pringletown beds of silt overlying that loose layer of black sand. Also note that in this particular case, we had what we call 4 coverage or 4 blast events that took place. Okay. What we did as far as instrumentation was survey the area before and after each blast. We performed pre- and post-blast CPTs, and then we also measured pore water pressures at 10 different locations, okay, both inside and outside the zone and at several depths, okay. We measured several depths within the zone and then right at the center of the loose layer outside the zone, and I've kind of indicated that here in the plan view, and then a cross section in the north-south direction below that in that B figure in the bottom right. Just to give you a sense of what occurred, I'm showing here on the left the excess pore water pressures that were induced by the detonation of the explosives, and as you can see within the loose black layer, we did liquefy the soil. I'm comparing it to the vertical effective stress, okay, there at the edge in the center of the zone. We did generate a little excess pore water pressure in the denser layer above, but significantly below liquefaction levels, okay. And then as these pore water pressures dissipated, and I'm trying to illustrate this here on the right at 3 different times, which include a half an hour, 5 hours, and then 24 hours after the blast, we're seeing this gradient develop, okay? And so on the right edge of this contour figure is the center of the zone, and then as you move left, we're going outside the zone. And so you see this radial gradient begin to develop. And so in this particular case, we only had radial drainage because the loose layer was confined by that silty clay layer above and the marl below. Settlements that were reported, we had upwards of over half a meter of settlement in some areas at this particular site, over a 3 to 3.5 meter layer, okay? And what we generally saw was this, as you'd see at most blast densification sites, is this bowl-shaped settlement profile, okay? That's indicated up there in the top left corner. A cross-section through the center of the zone shows the densification, or surface settlements, I should say, through the center of the zone after each blast. And generally speaking, the amount of improvement or amount of settlement that we shot, incremental settlement that we observed between each blast decreased, okay, with successive blasts. One question that might arise in people's minds is, okay, well, was the densification occurring within the loose layer itself? And again, we saw that we only liquefied that layer. And secondly, CPT results also show an approximately half-meter drop in these 2 layers, the overlying Waccamaw formation and then the black sand below. So that kind of helps verify that, yes, densification was only occurring within that black sand, all right? And that corresponds well with the surface settlements that we observed as well. So we're fairly convinced that, yes, densification was happening in that area. So really what we want to know is, okay, what kind of increase in penetration resistance might we expect? We had an estimation of relative density before the blast, anywhere from, say, 20 to 30%, and then relative density increasing based on those surface settlements to as much as 80+% at the center of the zone. Okay, and so we may expect, based on the stress levels at that depth, a tip resistance upwards of 15 to 20 MPa. But as you might expect, given this talk, we did not observe any increase in penetration resistance. Okay, in fact, we observed a decrease in penetration resistance at some locations. The only areas where we saw a slight increase in penetration resistance was actually outside the zone, or outside the blasted area, and that'll make more sense here in a second. Another interesting thing to note here is that we also noticed an increase in the pore water pressures. If you look at the CPT results, I'm showing the pore water pressures measured at the base of the cone, and they actually increased from pre-blast levels. Okay, and that was an interesting result, and I'll try and get to that here in a second. So one of the first things that we wanted to do to try and look at, whether or not, to try and explain why we're not getting an increase in penetration resistance was to see if we could look at the stresses. Okay, and so how we did this was with a finite element analysis. Now, trying to predict in a finite element framework the excess pore water pressures that are generated during a blast is extremely complex. Fortunately for us, we had really detailed pore water pressure measurements, and so we could input these measurements and use those as the driving force as they dissipated. And so if you look over here on the right, I'm showing the computed and measured dissipation of excess pore water pressures before and after each blast at a couple of locations. Okay, and so we did a pretty good job as far as matching up that dissipation. Okay. The second thing that we wanted to consider was our choice of a constitutive model to actually simulate the soil itself. And what we ended up going with was the sand hypoplasticity model, which is a critical state model that takes into account both, it has these barotropy and pycnotropy terms, which are just fancy ways of saying pressure and density dependence, okay, as is the case for soil. And we wanted to generally capture the behavior of this material at several different densities. And as you can see over here on the right, we do that with some triaxial tests. I'm showing the stress-strain response for several different relative densities, approximately 20 to 80%, and we capture that behavior reasonably well with this one model. Okay. The second thing we needed to do, which is a limitation of elastoplastic models, is capture that resedimentation process. In other words, we have to erase the stress history. And so with the basic sand hypoplasticity model, we can do this. And so if you look at this bottom right figure, this BSH, which stands for the basic sand hypoplasticity model, we wanted to resediment in virgin compression. Okay, but outside the zone where we didn't observe settlement and we didn't erase the stress history or liquefy it, we wanted to recompress with a denser state. Okay, or excuse me, recompress with a lower compressibility, or that recompression curve. And so for that, we use the extended sand hypoplasticity model. So that's how we were able to capture those two different behaviors. If I go ahead, if this animation works here, you get a sense of, okay, the settlements and where we computed settlements, and they follow pretty well with our measured deformations as well. The one thing that the model can't capture, of course, is the groundwater loss or water that's piping up in an artesian condition through the blast holes after each detonation, okay? But as liquefaction times decreased, our predicted and measured response were actually quite good, as you notice over here on the right, okay, over here on the right. So we reasonably captured the deformations as well. Oops. And so then let's go ahead and take a look at the stresses, as I mentioned before. And up in the top figure here, you're looking at the mean effective stresses before the blast, predicted before the blast, and then and below you're looking at the measured pore water pressures afterwards. And these red lines that you're seeing on the post-blast stresses are the CPT locations, okay? And you'll see that we get some arching and stress redistribution outside the zone, okay, where the material was stiffer, okay, where there was a stiffer response during reload and the material didn't liquefy. And this is also the area where we didn't observe a lot of settlement, but did observe a slight increase in penetration resistance. So you see that here with that CPT 11 or CPT 3 on the right side. Where we saw decreases in penetration resistance, we also saw or we computed lower stresses. So in that case, we're attributing this decrease in penetration resistance, at least in part, to lower stresses in the layer. And then at the center of the zone, interestingly enough, the stresses based on these computed results appear to come back to approximate pre-blast levels, okay? And that would be the 6-7 location at the center of the zone. But we did not observe a large increase in penetration resistance, okay? And so that's where we started to ask ourselves, okay, what's going on with the gas, okay? What's going on with the gas that's released during detonation of the explosives? So one of the instruments that we had out there to measure pore water pressures, so the BAP probe acts as both basically a piezometer, but it also has the ability to sample pore fluid. And I say pore fluid because to sample pore water, but also any potential free gas that may exist. So I'm not going to go over this in a large detail, but really what we're able to do is capture the pore water, and then with the gas that's in the headspace, we can quantify the amount of gas that was in situ, okay? And that's an important thing here for us to understand. So we wanted to understand, was there any free gas in the soil matrix that may be contributing to the post-blast penetration resistance? And so, of course, once we went out and sampled groundwater, the more groundwater that we sampled, we basically observed more gas in the container, okay, or more nitrogen. So the two reaction products from the hydramide 80 are basically nitrogen and carbon dioxide. Nitrogen being has a very low solubility, while carbon dioxide has a very high solubility. So it's nitrogen that we're really interested in as far as something that would contribute to free gas in the soil matrix, okay? And so as we sampled more groundwater, we got more gas. And on top of that, we wanted to say, okay, based on the amount of gas we have we saturated the groundwater with gas? In other words, we cannot dissolve any more gas and we would expect free gas, and the answer was yes. So we have this on the left here, water gas saturation, which we call ADA, and when that's above 100%, we say that we have free gas. And based on the amount of free gas, and we're not trying to say that we captured all the free gas that was in the area, only because some of it may have been trapped in the voids, that would give us degrees of saturation less than 100%, though they may have been lower than what's indicated here. So finally, let me finish up here quickly with a look at the pore water pressures that we typically expect around the cone. So with coarse sand, we typically do not expect any excess pore water pressure. But in fine sands, we do expect some excess pore water pressure around the tip and then at the shoulder, okay, as we observed in pre-blast as well. So when we have a gas in the soil, basically that will increase the compressibility or decrease the bolt stiffness of the material ahead of the cone. And that increased compressibility could contribute to the decreased penetration resistance that we observe as well after blasting. Additionally, as that cone passes, we also induce very large shear strains around the base, and in a dense material, we would expect negative excess pore water pressures. But what will happen when you have a gassy, dense material is you'll lose that negative excess pore water pressure that typically develops. And so what I'm showing here is the difference between shear strength of dense, saturated sand during shear and dense, gassy sand during shear, and you have a much lower penetration or a much lower shear strength because you're not developing those negative excess.
Dr. Gallant, we need to wrap up. Time is running out.
And that concludes that concludes my presentation here on ground improvements, on blast densification and verification of the improvement. So these two mechanisms are going to influence your penetration resistance. And so with that, I'll thank everyone for attending.
Thank you very much. Again, we are kind of running very tight here, so I'll go straight to the next presentation. This one is by Dr. Antonio Mariucci, and he'll be talking to us about soil liquefaction risk mitigation using earthquake drains, and a brief introduction of Dr. Mariucci here. He received a Ph.D. degree in civil engineering geotechnical from University of Texas, Austin, MBA degree from University of Rhode Island, and M.ASCE degree from Northeastern University. He's the managing director at D2C Strategist LLC in New York City, and he's also a research professor and adjunct lecturer at the Tandon School of Engineering at New York University. Dr. Mariucci.
Thank you, Jose. Good afternoon, all. All right, this afternoon I'm going to focus on soil liquefaction mitigation using earthquake drains. So quickly moving into the presentation. All right, so this afternoon what we'll be covering, just a quick overview, synopsis of liquefaction, moving over into how to use the vertical drainage for mitigation of liquefaction, components, the design, some results from small-scale and large-scale experiments, and then wrapping up with some summary and conclusions. All right, so starting off with liquefaction itself. All right, so when we have a loose granular soil and it is sheared either monotonically or dynamically, the soil particles are wanted to rearrange themselves into a denser packing, reduce the overall void space to take care of that loading that's happening. When we have saturated, undrained conditions, the soil can't densify itself, but rather pore water pressures are generated in response to that loading. The pore pressures are sustained when that rate of generation is greater than the dissipation. So this is where we're really focusing the discussion this afternoon. And if the shaking is large enough and long enough and the soil is loose enough, these excess pore water pressures that are generated may lead to liquefaction itself. So what is liquefaction, or how does it occur? It occurs granulated saturated soils when pore water pressures equal the initial vertical effective stress. What we get from that is a significant loss of shear strength and a loss of stiffness, excess deformations, and such. So, moving on. So what are we now looking at? Well, we do not need a full liquefaction to occur before we start to realize a significant loss of shear strength and stiffness. We start to see this when about 50 to 60% of the initial vertical effective stress is generated in that pore water pressure. And what researchers have found over time is that in low pore water pressures, everything, or the coefficient of volume compressibility is relatively low or linear. However, about 40 to 50%, or this pore pressure ratio about 0.5, 0.6, what we can see is this compressibility index really increases exponentially, and we start to see a lot of deformation occurring as that pore pressure increases. So what do? We try to limit the amount of pore water pressure generated in the deposit itself. Initially started with about only 40% pore water pressure generated. The Japanese back in 1998 had reduced it to about 0.3, and now currently here in the U.S. what we're looking at is a maximum average pore water pressure throughout the entire duration of shaking, as well as at any point in the deposit, looking at keeping that to a ratio of less than about 0.6, which keeps us in this low compressibility range of the graph, what we could see on the right-hand side of the slide. So, what are some of the consequences of liquefaction? Well, they include bearing capacity failure, development of sand boils, permanent vertical and lateral deformations, rotational instability, flow failures, etc. As we mentioned, we do not need that full liquefaction to occur before we start to see a lot of these deformational considerable ground settlement or deformation to exist or be realized. Stable soils could be potentially weakened as well as the pore water pressures are being dissipated from deeper in the deposit towards the surface in typical natural conditions without any drainage mechanisms in place. So now start looking at drains and what the topic of this afternoon's discussion is. So Vern Schaefer et al. Back in 2012 had reproduced this graph that you could see up on the screen in front of you relating grain size particle distribution versus percent finer by weight in various ground modifications that are used throughout the industry and where their applicable ranges are, keeping in mind that the end lines for each of the techniques are more recommendation than hard delineation mechanisms. So there are a bunch of different approaches that can be used. The gray area seen on the chart itself is soils that have been shown to be prone to liquefaction or had liquefied. We are focusing the topic on drains, which is predominantly within the sand layer. However, what we could see is liquefaction mitigation of these granular soils can be accomplished in a number of ways through densification of vibratory or dynamic means, reinforcement, solidification, or a binding of the soil particles. Our topic today, providing a drainage mechanism to dissipate the pore water pressure, and lastly, to isolate the potentially liquefiable soils and contain them. So the ultimate goal of all of these techniques is to speed up construction, strengthen the soils, stiffen the soils, reduce permeability, or provide a combination of effects. Okay, so natural conditions. So this is typical deposit, nothing has been done, what we're looking at before we even get in there. So once seismic event happens, excess pore water pressures are generated in the saturated, partially saturated soils due to some dynamic event or shearing. What we can see is significant dissipation of the excess pore pressure typically does not occur until after the excitation is ended, which can be considerable depending on where you are in earthquakes in that region. The ground surface can maybe be the only drainage boundary. As such, the water flow needs to occur vertically upwards. What we know through nature, especially onshore, is that the subsurface can be quite heterogeneous and layered, which means that interbeddedness of the layering can contain very low permeability soils which impede the flow, which now start to prohibit or prevent that dissipation. And the time required for dissipation can be considerably long, depending on the depth of or thickness of the deposit, the soil characteristics, the hydraulic properties, drainage characteristics of the soil. So here where we start to get into the topic of today. So permeability perpendicular to the bedding plane can be considerably lower. Researchers have shown this through numerous testing over the years. What we're doing is to expedite the drainage. What we're doing is shortening the drainage distance instead of going from somewhere in the deposit vertically to the surface. What we're looking to do is now put in vertical drains and now move the water radially, horizontally through a more permeable layer and get it out and keep the pore water pressure downward and dissipate more quickly. So keeping that dissipation used more rapidly, preventing a maximum buildup of excess pore water pressure, keeping the length of time at those elevated levels of pore water pressure, we're trying to minimize those. So as such, what we're looking to do is to keep the pore water pressure below a prescribed level. This way we can maintain our stiffness, we can maintain our strength, and reduce the deformations that may ensue. So what we look at, or how we look at this, is we're using a unit cell concept, as shown on the bottom right here, idealizing a vertical drain shown in blue, and there is an influence diameter around each of the drains, as we'll show on the next slide, shown here in this green color rather. And this tributary soil volume is actually what each drain is responsible for draining out of the deposit. Too fast. Okay, so typical vertical drains. Typically, drains can consist of either aggregate or gravel or crushed rock, or a geocomposite element, which is what we'll be discussing today or are discussing, typically arranged in a triangular or grid pattern. The spacing is determined based on some prescribed performance criteria. It's a function of the seismic event, soil, in situ soil characteristics, mainly permeability, and the maximum allowable pore water pressure based on our codes or common practice where we are. Even though the tributary area may form a rectangular or a hexagonal shape as shown on the two graphics on the right-hand side, we idealize this by using an equivalent diameter that D-effective as we saw on the prior screen, and analyze the flow through that idealized volume. What is an earthquake drain, or this prefabricated vertical drain for liquefaction? Well, what we have is a corrugated plastic pipe, nominal inside diameter ranging from about 3 to 8 inches. 4 inches is typically common, at least here in the U.S. Slotted perforations along the length of the pipe, and then a geotextile filter on the outside encasing the drain itself to prevent or minimize the flow of soil into the drain, preventing clogging itself. The key benefit of using these prefabricated drains is that the increased flow capacity within the drain itself. So we have high flow capacity, very high vertical hydraulic conductivity within the drain, very little or minimal resistance to flow, and it's quite inexpensive. How are they? Typically, drains are installed 4 to 7 feet center to center between the drains. Typically, a triangular grid is used. Contractors have reported depths of installation of about 60 feet, plus or minus, and typically use to install these elements utilizing some sort of a vibratory hammer on top of a steel mandrel. A triangular mandrel is shown up on the screen itself. Installing these into the ground. The photo on the upper right is showing labor installing or pushing the prefabricated vertical drain within the mandrel, getting ready to insert it into the ground. And if vibrations are used to install the drain itself, densification of the granular deposit typically ensues. So just quickly to go over how the drains themselves are designed. Initially, the work that was performed by both Booker and then Inoue et al. Had looked at gravel drains. So first with Booker, no well resistance. Once the water got into the drain, it essentially disappeared. So it was infinitely permeable. Later on, Inoue et al. Had incorporated well resistance, which decreased the flow capacity of the drain. The Japanese had modified both earlier approaches and cleaned up the design charts that both Booker and Inoue et al. Had developed. The more common approach that we're seeing now is through FEQ drain, which is a robust finite element modeling program, incorporates flow through the soil, through the orifice of the drain and within the drain itself. And then more work is currently being done on more robust, comprehensive finite element programs by Vitiniotis and Whittle at MIT, looking at more constitutive soil models, looking at complex geometries, complex slopes. Okay, so just another little overview looking at it so we can model, this is the FEQ drain, model very heterogeneous soils, different boundary conditions, different storage, different hydraulic conductivities, much more robust than the earlier design charts by Booker and then Inoue et al. Okay, so getting now into some of the results from small-scale centrifuge testing performed at UC Davis in California. 3 different models were tested. The first test was comparing an untreated side versus a drain-treated side. The second test was looking at the effects of pinning due to the materials used. And then the third testing that was performed was looking at untreated deposit versus tubes that were used, which did not have perforations to allow drainage, and then drains, all in the same model. So some of the concerns we were looking at is soil pinning, density effects, harmonic versus sinusoidal type motions, looking at the responses of the ground, or the model looking at accelerations, pore water pressure generation, and deformations. Okay, so some of the results. So this is the first model that was put through, comparing along an idealized center line, two sloping geometries coming towards the center. The bottom layer was a dense layer, just basically there to help promote the saturation of the deposit. A thicker liquefiable layer in the middle, loose sand, and then this crust to prevent or slow down the dissipation of pore water during the testing. And what was realized during the test was there was a 20 to 50% reduction in pore water pressure generation, 60 to 70% reduction in vertical settlements, and between 80 and 90+% in horizontal deformation between the drain-treated and the untreated side. But the question came out of soil pinning. So how did it work? What was going on? Oop. Jumped in too fast here. Okay. So on the second test itself, looking at the effect of the different types of material and looking at if they had a pinning effect, more on the looking at results, did it affect the drainage characteristics and settlement profile. So what we saw was still similar 20 to 50% reduction in pore water pressure generation, much lower vertical and horizontal settlements, which resulted in the type of material used in these testing really mattered. And if it slightly over stiff, definitely contributed to a pinning effect, but did not affect the pore water pressure dissipation. So these are here on the left-hand side looking at the results of the deformation that were realized in this first test. So much considerably less vertical and lateral deformations for the 5 sinusoidal motions that were used from 0.01 G to 0.35 G. Oops. Keep hitting the wrong button. Looking at the acceleration, so base input motion. On the treated side with the drains, what we saw was the motion was carried up to the surface. Dilatancy spikes were realized. However, we did not see a full loss of input motion as we did see on the untreated side, where we hit large pore water pressures, but we lost complete signal. So moving on to model test number 3, so looking at 3 different sections oriented at 90 degrees. And basically what had been realized were the drains were flexible, did not impact the response. Drains were very effective in dissipating pore water pressures. The input motion and the types of drains were very sensitive to the results that were obtained, in that the deformations really started increasing considerably once we exceeded this maximum average pore water pressure about 0.5.
Dr. Mariucci, about 1 minute left.
Okay, so sorry folks, going to have to skip over the field portion. Just going very quickly, just showing something here that would be of interest. So looking at the effect of the drains in the field, what we had noticed that we had realized both pore water pressure response beneficial during the installation of drains from one to another. What we had seen as communication and the dissipation during installation. We had predominant benefit due to densification of the soil deposit. After a couple of drains were installed, what we had seen is a much better response, a lot of pore water pressure coming out of the ground, dissipation during installation, vertical strains or settlements about in the 5 to 6 inch range, which resulted in 1 to 2% vertical settlements. So just ending up with some thoughts. Vertical drains, increased dissipation which resulted in a decreased maximum buildup of pore water pressure, decreased the potential for strength loss, volume change, excess deformations, and decreased shear strains, which increased the soil stiffness throughout the entire excitation. Very inexpensive treatment, about $3 to $5 per linear foot of pipe installed. Additional cost for a vertical surface bedding layer and any surface piping needed. Thank you.
Thank you. We'll move along here because we are pretty much using the time for each speaker. So there's some time left at the end. We'll look at questions. The next presentation or presenter is Sonia Swift, and she'll be talking to us about the use of rigid inclusions to support large spans. Brief introduction. Sonia has a BS and M.ASCE degrees in civil engineering from Tufts University, and she's currently the regional design manager at Menard, USA. Sonia, you have the floor.
Great, thank you. All right, so today I wanted to talk a little bit about the use of rigid inclusions to support large spans, and the case study that I'm going to be talking about is the South Capitol Street Bridge Project, which is a large project that is currently underway in Washington, D.C. It's about $1 billion project or so, and it includes the replacement of the Frederick Douglass Memorial Bridge, the construction of 2 approach ovals, the east and west on either side of the Anacostia River, as well as a number of different construction ramps, traffic ramps that are going to be constructed, some of which are permanent and some will be temporary. The soils at the site include thick deposits of soft alluvial soils that, if left untreated, would have resulted in large settlements because they are raising the grade quite significantly, sometimes up to 20 or 30 feet during this construction. One of the places that the ground elevation is being raised is over some critical structures that they're calling the twin utilities. These are 2 side-by-side concrete structures. They're unreinforced concrete, and they're, running directly underneath the east oval construction. Here's what the conditions at the twin utility look like right now. You have the 2 structures that are side by side. You can see that they're supported on piles now. They're actually timber piles that are extending into a layer of medium dense sand, which is a terrace deposit. You can see that up above that sand layer, there is a soft alluvium layer and then a sandy lean clay at the surface. What they're planning to do, the final condition is going to look something like this. They're putting somewhere around 17 feet of fill on top of this area, and it is going to be subjected to traffic loads as well. And so the final condition, in order to protect the twin utility from these loads in the subsequent settlement, needs to look something like this. The challenge is figuring out exactly how to construct and design that in a way that makes the most sense and is economical. The embankments adjacent to these twin utilities were being supported with rigid inclusions. But the twin utilities themselves couldn't settle. There was very strict criteria on the amount of settlement that they could be subjected to, as well as the additional stress that these utilities could see. And essentially, we worked with the owner, but essentially the numbers were 0. They could experience no settlement or additional stress. Because of the width of the utilities themselves and the clearance that we needed to keep from those outermost piles, the actual span ended up being about 62 feet. So you can imagine a traditional reinforced concrete slab really wasn't going to do the job here. So along with the contractor, the general contractor, and the utility owner, we talked about a number of different solutions, including a bunch of different types of beams to span this area, lightweight fill, geofoam, and combinations of these different solutions. What we ended up doing was teaming with SAI consultants from Pittsburgh, which was a structural engineer for this solution. And then we worked with them along with South Capitol Bridge, who is the general contractor for the South Capitol Street project. And we designed a two-part solution using adjacent box beams and steel beams. For the most part, box beams were used to span the utility all along the run here, but at the edge where the utility or the protection system is going to intersect the oval, we did use some steel beams just because of the geometry there. The beams that run perpendicular to the utility are sitting on two concrete grade beams that are running parallel to the utility, and those grade beams are, I believe, 2 feet by 3 feet. So fairly small grade beams supporting those box beams. Overall, the area ended up being about 64.5 feet wide and 182 feet long, and there were a total of 77 rigid inclusions beneath it. Sorry. So just a few more of the structural details. They were 48-inch square pre-stressed concrete box beams that we used. The box beams were doweled into the grade beam below it to prevent any type of lateral movement of the grade beam of the box beams. But the grade beams were not attached to the rigid inclusions in any way. They were just sitting on top of the rigid inclusions. And I apologize, I noticed this morning that I left CMCs in there. CMCs is Menard's proprietary name for rigid inclusions, but it means the same thing. And so it became, so the structural portion of the box beam system was one aspect. The other aspect of it was designing the rigid inclusion system to provide the support that was required to meet the project criteria from a settlement standpoint, and also to design the rigid inclusion structurally to be able to take the loads from this large span. So we created a 3D Plaxis model to evaluate both the settlement of the system and the forces in the rigid inclusions. The main thing that we focused on was the differential settlement, and that was really where we tinkered with the design to get it to work best. As you can imagine, you've got this very stiff system where the utility protection system is, and then on the sides, the rigid inclusions supporting the embankment are going to be providing a much softer response. So what we wanted to do was minimize that differential settlement so that at the ground surface, the response was uniform or nearly uniform. The results of our Plaxis model here, you can see it on the right. Up above, we were getting about 0.15 inches of settlement at the center of the utility protection system, and then that increased to close to an inch, about 0.8 inches or so, out at the edge. And the way that we did that, again, was just by spacing the rigid inclusions out wider and wider as you moved away from the utility protection system. So the second portion of the geotechnical design was looking at the loads, and you can see that the loads in the rigid inclusion supporting the embankment range from 50 kips or so to 90 kips. They're pretty reasonable, and those are terminating up in that terrace layer where the timber pile foundations are. But the forces in the CMCs underneath the utility protection system were much, much higher. We're seeing forces of about 290 kips, and these rigid inclusions were spaced about 4.5 feet on center into the page. So when we actually did geotechnical capacity calcs to make sure that we were okay at the depths that we were anticipating installing them, we were getting factors of safety of about 1. While this was a little concerning, our general experience shows that our load tests will perform better in the type of soil that we were in. So we moved forward knowing that if the load test didn't perform as well as we expected, we would anticipate drilling deeper. So we went into the field to install these. The rigid inclusions under the embankment were unreinforced 12-inch diameter elements, while the rigid inclusions under the utility were 18 inches in diameter, and they were reinforced with a central reinforcing bar. The exact location and the condition of the top of the rigid inclusion were critical here because that grade beam was going to be sitting directly on top of our elements. It really needed to be a flat, smooth surface, and in order to not impact the design of the grade beam itself structurally, the rigid inclusions needed to be exactly where we anticipated them to be. So our field team did a fantastic job. Took a lot of extra precaution to make sure that these elements were exactly where they needed to be. You can see those steel cans that they used to put around every CMC so that they knew where they were drilling the elements. And the utility owner was very involved during installation of the elements. They were performing monitoring, and we were communicating with them on a daily basis to make sure that everybody was comfortable with how things were progressing. Okay, some quick photos from construction. Here on the left, you can see that there are those metal cans at different locations just so the drillers could move from one location to the other pretty quickly and know that they were exactly in the right spot. And then there on the right, you can see they're putting those monstrous box beams into place. And on the next slide, here we have our load test apparatus, the test frame all set up and ready to go. This was a larger frame than we use for our typical load test. This frame could go up to 600 kips because we knew we were testing to some higher loads. Here is actually the result of the load test that we performed. Again, this was on an 18-inch element that was installed into the Potomac layer. We were able to apply a maximum of 580 kips, which was 200% of the design load, and at that load we saw 0.4 inches of movement. So we stopped the test at that load because we had reached the capacity of the frame, not because of the geotechnical capacity of the element. At the design load of 290 kips, we were seeing about 0.15-inch movement. We were pretty happy with those results, and we actually were able to get some good geotechnical data about all of the soil layers from this test and some other load tests that we performed at the site. We put strain gauges in the element at 6 different locations, kind of strategically placed around changes in the soil layers so that we could evaluate the frictional capacity of the different soil layers and bearing capacity. We used those throughout the project when elements came into question, or also to optimize the depth in certain areas. And it was interesting. We did this for a few different load tests, and we did find that the frictional capacities matched up very well from test to test across the site. So to summarize what we learned from this and how we moved forward using the results of the load test, we had designed for a rigid inclusion length of about 58 feet at the twin utilities, and we moved forward using that same length after the test as well. The load test did perform better than we had estimated for the hand calculations, so we moved forward knowing that we felt pretty comfortable, even though these loads were much higher than what the loads that we typically use for rigid inclusions. The benefit to the contractor, South Capitol Bridge, was that they didn't have to mobilize additional crews or rigs or work with another subcontractor. They were able to use rigid inclusions under this fragile structure just as they had under the adjacent embankments. And because the rigid inclusions weren't tied into the slab, the construction was made significantly easier. It was a little bit harder on our end, but once we were done, they were able to move pretty quickly on top of the rigid inclusions. And it was kind of a unique experience with the utility owner and the structural engineer and the contractor, because we were really in constant communication and requiring approval at every step of the way, both during design and the installation of these elements. So it was an interesting use of rigid inclusions and a little bit more complex than what we typically do. That's actually all I have for you guys. I don't know if anyone has any questions.
Thank you, Sonia. I think what I'm going to do, thank you for finishing a little ahead of time. So we have a few minutes, but instead of entertaining questions now, perhaps we'll go to the last speaker, and then if there's some time left at the end, we'll go to the questions. So the next and last speaker is Dr. Leon van Paassen, and he'll be talking to us about field trials on microbially induced desaturation and precipitation for liquefaction mitigation. And a brief introduction for Dr. van Paassen. He received a master's degree in applied earth sciences from Delft University of Technology in the Netherlands, and he later obtained his doctorate in applied sciences at the Department of Biotechnology, also of Delft University of Technology. He's currently an associate professor at Arizona State University, and he's also a senior investigator at the National Science Foundation Engineering Research Center for Biomediated and Bio-Inspired Geotechniques. Dr. van Paassen, you have the floor.
Thank you, Jose. Let me see if I can upload my slide deck. Just select here. No, just click it, right? How do I upload the slide deck again?
Just click on your slide deck.
All right, here we go. Here we go.
Okay.
Yes. Thank you. So thanks, Jose, for the introduction. I'll try to stick on time as well. So what we do here on the biomediated or bio-based ground improvements methods, the technologies we're investigating at the Center for Biomediated and Bio-Inspired Geotechniques, we try to stimulate the biology in the ground to improve our ground properties. So in doing so, we can use either a biological agent to do a chemical conversion, and we typically bring in some food to stimulate the native microbes, and they produce a product, and the product can either be a mineral, or it can be some organic matter, or it can be some biogenic gas. And by controlling the amount and the location of those products, we can change the mechanical properties of the subsurface. So last year I also gave a lecture here on using microbes to stimulate carbonate precipitation in order to cement the soil and increase the shear strength or stiffness or increase the dilatancy. But this year I will talk about another process in which we use denitrification, which is the reduction of nitrate, to desaturate the soil with nitrogen gas and also precipitate calcium carbonate in the meantime. So how does this process work? The process of denitrification. Well, in this case, you need some substrates which contain calcium, nitrate, and acetate, or another organic carbon source. If you pump them in the ground in a soluble state, then the bacteria which are in there, which are already in the ground, they use those substrates to grow, to create more biomass, or to precipitate minerals, or to generate biogenic gas. So as mentioned, the minerals, if you form minerals between the existing grains, you may increase strength, stiffness, density, dilatancy, or reduce porosity and permeability. The biomass itself, it's not really having a lot of effect on the strength and stiffness, but it does reduce porosity permeability, whereas the nitrogen gas, it would reduce saturation. But then if you reduce the saturation, we will see that we can also increase our cyclic shear resistance. But also we can reduce our permeability. So these processes have been developed in the lab for the last 10 years, but in the last 2 years we were able to go outside and we found some project locations and found some contractors and clients to work with us. In 2017, the summer of 2017, we did a field trial in Toronto in the Portland area where we tried to stimulate the denide fighting bacteria in the subsurface to do a ground improvement. Well, here you can see the well design. In Toronto, we used 6 injection wells surrounding a single extraction well in the center. And we did 3 plots. In each plot, we varied the amount of substrates we injected. And we tried to cement the soil, or treat the soil and cement it or generating biogas. So we try to close the water balance, so just extract water to prepare your solutions and then pump them back in again. And we did so using 12 weeks of continuous injection of the substrate solutions. So in total, we injected about 80 cubic meters of substrates into the ground in a period of 3 months. So it's a very relatively low flow rate. One of the reasons for that was that the soil was actually quite silty, so the permeability was already pretty low, so we could not apply very high flow rates. Once we injected everything, we did some test trials. So within our test trenches, in the trenches we excavated, we found that in the treated area, the trench was pretty stable, whereas in the untreated area, which was adjacent to the treated zone, the soil profile typically collapsed. However, this is not really direct evidence that what we actually treated was responsible for the more stable surface. I mean, it could also be like capillary pressures or other things which keep the trench upright. Other means of testing what really happened was looking at the sensors which we hang in the extraction wells. They were fully covered by calcium carbonate, indicating that precipitation did take place. Also, we took samples and we tested for calcium carbonate. While injecting, we also did some measurements. We placed some sensors at different depths in the ground, and these sensors are able to measure the volumetric water content, which is then a proxy for saturation, and also they are able to measure salinity, which is a proxy for the amount of soluble substrates which are still on the subsurface. If those substrates are consumed, the salinity would go down to 0. So what you can see in this plot is the measured volumetric water content, and typically if you look at the yellow and the blue lines, it is gradually reducing in time, which indicates desaturation. The orange and the gray line here, those are sensors which actually you see these spikes of increasing volumetric water content. We still don't have a really clear clue what happened, but we have some indication that we did some hydrofracking here. So because the volumetric water content is a complex parameter which combines desaturation and porosity, we expect that here we frack the soil a little bit and then you get an increase in porosity and also an increase in saturation as a result of that. Next is the monitoring results. When we did some CPTs in the area, both before and after treatment, actually it was very hard to see whether there was any treatment. Well, what you can also notify in these profiles is that typically the treated zones contain a lot of clay and silty sands and sandy clays, which are pretty low permeability, so it's very hard to inject anything there. Most likely, most of the injected substrates, which were injected between a depth of 1 and 5 meters, probably mostly flush through the actual upper sand layers. When we looked for shear wave velocities, clearly, well, I'm not sure if you can see anything here, but I didn't see any significant increment in shear wave velocity. But then if we look further and looked at the P wave velocities, which were also measured using the seismic CPT, we could see that in the treated areas, the unimproved, the blue lines here are the unimproved zone. the orange lines in most locations show a reduction in this P-wave velocity, which indicates that although we may not have seen an increase in shear wave velocity, which should correspond to an increased strength or stiffness, we do see an increase in P-wave velocity, which shows a decrease in saturation. So, seeing this concept of reduced P-wave velocity, we considered, well, maybe the cementation didn't work that well, but the desaturation probably does work. And then moving forward, we considered, well, you can actually increase the cyclic shear resistance by cementing the soil and increasing the stiffness. But if you desaturate the soil, then the presence of the gas phase is also preventing pore pressure buildup to occur. And if you then compare the two outcomes of the same process, either aiming for cementation, we originally considered that in order to stimulate sufficient strengthening, we should precipitate about 1 to 3% of calcite. Well, in order to present that, we needed about 25 to 70 kilograms of substrate per cubic meter of treated soil. And in order to inject this in the ground, we probably need to flush the soil 3 to 10 times with the total pore volume to get this 1 to 3% of calcium carbonate cementation using the denitrification process. But if you aim for desaturation, probably 10 to 20% desaturation is enough to increase the cyclic shear resistance sufficiently. So because the nitrogen gas is much more voluminous than the calcium carbonate minerals, you need much less substrate to achieve that amount of desaturation. So actually you need less than 1.5 kilograms of substrate per cubic meter of treated soil, and you can implement everything in a single flush. So comparing desaturation with precipitation, obviously it shows the advantage of desaturation in the amount of required resources, which is 40 times less than what you would require with calcium carbonate cementation. So having this in mind, we found a second location actually in close to the city of Portland. So in the city of Portland, typically the area is full with liquefiable soil. So all the purple areas here, they're potentially liquefiable in case of a magnitude 9 Cascadia earthquake, which could occur in that area. So they found there's the need to do something about this, and particularly if you then look for sites where there's already existing infrastructure, things like densification or ground improvement underneath existing structures may be less suitable for those locations. Then we considered if we are able to desaturate, and particularly if we have a sandy soil which is relatively permeable, we can inject our substrates over larger distances and thereby also treat underneath existing structures. So having this in mind, we found two locations with a lot of collaborators here where you could try the concept of desaturation. So for this location, the actual site looks a bit like this. So here you can see the Sunderland site, which is very close to Portland International Airport, which is also placed on liquefiable soils. So here you see the total setup for a single field trial, where this is our office, and here you see some vessels where we prepare our substrate solutions. Once we prepare the substrate solutions, we can inject them in the ground, and for this particular application, we turned the direction of flow around. So we injected from the center and we extracted water from the surrounding wells. If you would extrapolate this to an actual application, then you may change the well configuration or do more linear type of injection. In order to see what would happen in this case, we installed several monitoring instruments. So again, we installed those volumetric water content and salinity sensors downhole. And also here we installed some crosshole sensors, some sensors to do crosshole seismics in the same area. And we also mobilized using a rapid grant from NSF to mobilize the big shaker from Texas A&M to do shallow liquefaction analysis. So so we had TIROS 12 sensors. We had those VP, VS crosshole measurements We did shaking analysis, and then we used some CTD divers to measure in the well the salinity and the volume of extracted liquid. So in terms of extracted liquids here, you see here now we only took one month, maybe 5 to 6 weeks to inject a total of, well, in this case it's in gallons, but here it's about 60% of the originally intended pore fluid. Then when we, so after a week or two, we found that in the same area that actually the saturation was reducing, and here we could indicate that the saturation was decreasing by a decrease in pore wave velocity, and then we reached like a very low pore pressure wave velocity in that area after 2 weeks, and this indicates there is sufficient desaturation, at least 5 to 10% desaturation is in the same area. At the same time, we didn't see any significant change in shear wave velocity, so it's the effect of MIDP in this case, or microbially induced desaturation and precipitation, mostly focus on the desaturation part. Looking at some TEROS 12 sensors, we could now try to find an idea about the saturation. So here we installed several sensors at different depths, and we could monitor that the saturation actually reduced to about 92 to 90%, while at the same time here again you see a spike in salinity indicating there may be some shallow hydrologic fracturing occurring in the area, but you see in general an increase in salinity indicating that there are substrates being distributed throughout the treated area. So this is all pretty preliminary information because the Portland field trial has been performed just last summer. We're still interpreting the information which we're gathering at the moment. Also, we're continuing to monitor what happens with the desaturation, because if I will conclude here, I would say yes, we were able to inject substrates over a large distance. So we can inject it, well, depending on, obviously on the permeability of the soil, up to a distance over 3.5 meters from an injection well. Well, desaturation is significantly cheaper than precipitation. We are able to monitor the results through downhole salinity sensors or doing P-wave analysis. And second, originally we targeted to desaturate sandy soils. But in this case, we had silty soils, and also in silty soils, it showed the P-wave velocity at least showed, and also the polymetric water content results showed that we are also able to desaturate relatively fine-grained materials. One of the things to consider is that when you're injecting in a heterogeneous soil, so obviously the liquids will go through the more permeable layers, so you will get some preferential path between the injection and extraction wells, and you're probably treating the most permeable layers in the first place. You could argue that after some time, once the gas fills up the more permeable zones, the liquid is forced to go through the lesser permeable zones, and still you get some substrates at the lower permeability locations. But as a result of this heterogeneous soil profiles, your gas distribution will also be heterogeneous within the soil. Next question is that a problem, right? How is the liquefaction resistance affected in a heterogeneous profile? Is it okay if locally there may be some pore pressure buildup, but if there's a neighboring gas pocket, that will dampen still these pore pressure buildup for the larger scale? So what's next? We took a lot of samples from both sides. We're planning to do some cyclic lab testing, try to characterize the excess pore pressure generation and shear strain curves at different saturation levels. We further have to look on the cyclic behavior. So this is all the cyclic lab testing we're planning to do. As the sensors are still in place, so we continue to monitor developments of P-wave velocity and also saturation and salinity, just to see what is the longevity of the gas phase in the soil. Does it eventually dissolve and diffuse to other areas, and how long can you leave it like this, or should you maybe apply a second flush or something like that? So we also just did, we don't have the results yet, CPT profiles of the treated area in the Portland location. And if I just listened very carefully to the talk about from Aaron, there are means to interpret those CPT results to assess whether there's gas present or not. With that, I would like to conclude, and I'm also want to thank all my collaborators in both projects, and I'm open for questions.
Thank you, Dr. Van Paassen. We have about 5 minutes left. I think we can go back and look at the questions and see how do we do that. Nadia, I need help here. I thought the questions would be here. So is Nadia and Christina still on the line, or? Answer questions.
Nadia is not with us.
Yeah, I'm not finding any. I'm clicking on the Q&A and I'm not finding any. Okay, let me see, refresh. I don't see any questions there. Here. I don't see anything there either. Refresh here again. I see no questions, so I think we will close this session here. I want to thank all the speakers again, everybody who signed up, and a special word of thanks to our gold sponsor, Keller Foundations. So I will close this session. Thank you, everybody, again. And hopefully there will be another one in the near future. Thank you.
Thank you.
Bye-bye.
Thank you. Ladies and gentlemen, that concludes your conference call for today. You may now disconnect. Thank you for joining and enjoy the rest of your day.